So let's start the recording as well. Okay, let's get started. Hello, everyone, and welcome to the second ISCARSAH webinar on earthquakes and traditional construction. My name is Tim Michiels, and I am a structural engineer at Old Structures Engineering in New York and an adjunct professor at Columbia University. Today's webinar is brought to you by, there we go, by ISCARSAH, or the International Scientific Committee on the Analysis and Restoration of Structures of Architectural Heritage. While more people join, I want to briefly introduce our scientific committee. We are an international group of engineers, scientists, and educators dedicated to the restoration and care of built heritage. We focus on the structural and technical aspects of conservation of architectural heritage. We have an elected board. Our president is Gorun Arun, and our secretary general is Tom Morrison. He is leading the discussion in the chat today. The goals of ISCARSAH are, amongst others, to disseminate knowledge, promote international cooperation, and organize international training programs. Another goal is to collaborate with other scientific committees, and we are happy to welcome members from a wide variety of ICOMOS committees attending today. In the past years, ISCARSAH has published Principles for the Analysis of Conservation and Structural Restoration of Architectural Heritage. We publish newsletters and currently are developing guidelines for the analysis and restoration of heritage structures. Pre-pandemic, we were organizing yearly workshops. The latest one was in, the latest ones were in Korea, Turkey, and the very latest one in Iran. You can reach us on iscarsah@gmail.com, follow us on Facebook, or find our website. Okay, that brings us to our webinar on traditional construction and earthquakes. In this webinar series, we are highlighting traditional structures because these buildings are often seen as the most vulnerable to earthquakes. Often, though, these buildings have seismic mitigation strategies built in as part of their original construction or past repair. Unfortunately, the built-in knowledge has sometimes been lost or is misunderstood. And thus, as safekeepers of old buildings in earthquake areas, we all grapple with the same question. How do we ensure the life safety of the users of a building while also making sure that that building is preserved with all its valuable features for future generations? Sometimes engineers take a conservative approach that tries to maximize structural strength, yet they go well beyond what is actually needed to ensure life safety. Often, this damages valuable elements of the building, and those well-meaning interventions might paradoxically in the end provide or contribute to a building's destruction. Additionally, the regulatory framework provided by building codes to properly deal with traditional buildings is often lacking. Thus, we need to study, learn, and discuss traditional architecture, and that's why we are here today. Building technology in seismic regions has evolved over centuries, leading to local seismic cultures. Today, we have another 5 distinguished speakers who will discuss the local seismic cultures they work on. We also hope to hear from you. We look forward to taking your questions after all the presentations. Please feel free to post them in the Q&A section at any time. You can also upvote questions that you would like to see answered from other people. We would also already like to let you know that a third and final seminar on this topic is scheduled for Thursday, April 14th. And in that webinar, we will have speakers talking about Kashmir, Greece, Iran, Nepal, and Pakistan. So mark your calendars for Thursday, April 14th. Then before handing over the floor to our speakers, I would like to thank Evan Spear and Tom Morrison, who are my co-hosts today. I would also like to thank the other members of the organizing webinar committee, Steve Kelly, Kai Weisse, Gorun Arun, Grigor Angeliou, Chula Akintudine, Stacy Vallis, and Maya Segara Lagunes. Finally, I would like to thank all of you, distinguished speakers, for agreeing to share your work with us today. Okay, so then without any further ado, I would like to introduce you to our first speaker, Stephen J. Kelly. Steve is an architect and engineer who has devoted these skills to the preservation of our built cultural heritage. With 40 years of experience, his projects range from small to immense, simple to sophisticated, and cover a wide range of building materials and systems. His projects are located throughout the US, Europe, the Middle East, Asia, and North Africa. Steve is a fellow of the American Institute of Architects, the Association of Preservation Technology, and US ICOMOS. He is a UNESCO Tangible Heritage expert and is the former president of ISCARSAH, serving from 2008 to 2014. Steve, welcome.
Thank you very much. I hope everybody can hear me okay and you can see my screen. Yes, I've worked on large projects, but I'm going to talk about some of my smaller and very interesting projects that I've done. I've called this presentation this morning "Tale of Two Regions." That's a takeoff on A Tale of Two Cities, a well-known novel. But today I'm going to talk about Haiti and Bhutan. Also, I wanted to put a shout out to the World Monuments
Sorry to
Fund.
interrupt. Can you put your presentation full screen, please?
Oh, you can't see it?
Yes, I can see it, but go to Window or View and then full screen.
View.
Full screen mode. Thank you
Lovely.
very much.
Thank you very much. I wanted to give a shout out to the World Monuments Fund because many of the projects, two of the projects I'm talking about, I did through the World Monuments Fund. But the first area that we're going to speak about is the island nation of Haiti. Haiti shares the island of Hispaniola with the Dominican Republic. You can see this is my country, the United States, Cuba, Mexico over here, and the South American continent. And talking about projects in Port-au-Prince, the capital of Haiti. Haiti has a very interesting history. The Europeans landed on the island in the 17th century. They enslaved the Taino population. It turned out that the indigenous people there were not very hardy as slaves, and they were decimated. And that was when the slave trade started from the west coast of Africa down here. Enslaved people were brought from the west coast of Africa, and at a time it was like 10 enslaved people to one colonist. The interesting thing that happened in Haiti, however, is they had a successful slave rebellion that happened in 1799, and this is a very important part of the character of the people in that island, is that they've had their freedom for 200 years. It's a very interesting place. But we're going to be talking about the earthquake and aftermath of the earthquake, which occurred in January of 2010. It was a 7.0 magnitude earthquake that killed between 200,000 and 300,000 people and left 3 million homeless. It was a humanitarian disaster. We first went there as a World Monuments Fund group in April of 2010, and I've been back to the island more than 10 times. The last time actually just about a year ago, right before the pandemic hit. So what I'm going to talk about is the gingerbread houses of Port-au-Prince. And when we went in 2010, there were about 300 gingerbread houses. They were all built from the 1880s to the 1920s. We looked at about 200 of them, and there are about 150 remaining. The construction types that are well known for Haitian gingerbread houses are, number one, timber frame or pan de bois, wattle and daub or colombage, and unreinforced masonry bearing walls. The mortar that's used is a mixture of clay and lime, and the wood was locally harvested. And so the first part, the timber frame, I think that many of you are familiar with this type of construction. This is a wood construction that has a brace frame in it. And there's an example of a gingerbread house with made mostly from timber frame. And then there's the colombage, or wattle and daub. This is a timber frame building where the infill is filled with either a rubble, with stone, or with brick. And then the third kind is the unreinforced masonry. And as you can imagine, the unreinforced masonry did not do as well during the earthquake as the pan de bois or the colombage. And this is an example of some of the larger buildings. And many of the strictly out of masonry are still standing as wrecks, and they have not been restored. An interesting aspect of this is that you don't see these three distinct types. They're all mixed together. This is a good example with this particular building that has an unreinforced masonry first level. The second level is colombage, and the third level is brace frame. And of course, I have to mention that after 1925, when wood construction was banned in Port-au-Prince, there were a lot of either concrete block or reinforced masonry structures that were built next to, as an addition to many of these buildings. These building forms did not work well together, and that was some of the things that we saw when we were doing our first assessment, but that's going to be a talk for another time. Because this morning I'm going to talk about two buildings in Port-au-Prince. One is the Maison du Fort, which we first visited in 2010. This is a photograph of it maybe a year after the earthquake. But the interesting thing that we saw with this particular building is the first floor, which was unreinforced masonry, was entirely destroyed. And you can see the condition. We were able to go up those stairs very carefully, and we found that the second floor was in fair condition. And I'm going to have to give a shout out to our colleague, Randolph Langenbach, who we were with. And Randolph was the person who noted that we had these horizontal metal ties in just about all of these unreinforced masonry gingerbread houses that we saw. And they had these wonderful fleur-de-lis patterns where they came outside of the building. And at this here is from the Maison du Fort. And this is one of the reasons why the Maison du Fort didn't entirely collapse, is because these masonry ties were holding up these corner piers. If these corner piers had collapsed, the building would have just fallen onto the ground. And so Randolph came up with this idea that since labor was fairly inexpensive in Haiti, that what we should do is we should hold up the second floor with emergency shoring, and then reconstruct the first floor unreinforced masonry. We came up with this idea of putting in new horizontal ties. Although we were going to put in many more horizontal ties, we made them out of stainless steel. And here is a stainless steel plate that we had fabricated in Miami. We cut it using lasers. And you can see that this was about the same size as that. You'll be able to see some of those where we put them in. So we came up with this scheme to hold the second floor in place. And we worked with our partners, the Institut de Patrimoine Wallon, which is out of Belgium, the southern part of Belgium. And they were maisonniers and charpentiers, and they came in and they were working with the drawings that we were providing with our local architectural partner. And this is the idea that we came up with. Now you can see that this is a drawing of the reconstructed first floor walls. And here we're adding in these horizontal ties. And instead of just putting one in at the top, we put in 1, 2, 3, 4 layers of them. And the second layer actually goes through the spring point of the arches of the first floor. Of course, it takes a village to do this type of project. So you can see in this photograph her Haitian workers and architects, partners from Belgium and France and from the United States. And we were all working together on this particular project. And here is the building with the first floor removed and the second floor held in place. It was not moved, it was left in place. We had to do some work on the foundations, which I will show you. There was plenty of brick to be salvaged. You can see piles of foreground that our local counterpart was purchasing and having it delivered onto the site. Here is the foundation system. This is the only place where we introduced reinforced concrete into the project. The original foundations are rubble stone laid in clay, and we poured a grade beam on top of the foundation system, but below grade, and that this is what we used as a basis to erect the new masonry walls. The photograph of this gentleman here, this is Patrick Lacroix from the Institut de Patrimoine Wallon. He was our mason, and he was actually doing a capacity building exercise, teaching local masons how to work with lime mortars. So we put the whole thing up with lime mortars. Here you can see the walls almost being erected. And if you look here, you can see the fleur-de-lis pattern. And here are the walls ready to receive the second floor. I wanted to run these horizontal stainless steel ties through all of these arch spring points, but Madame Pierre Louis would not have it. She agreed that I could do it in one area. I always like to show what the intervention is, and she allowed us to do it in this one particular area. And so this is what the building looks like, fully restored. This is during one of my visits on another project in 2017. And this has become an art gallery and a venue for music and art performances. And you can see that we were able to develop this very open atmosphere. By the way, this building was built by Haitian architects who were trained in Paris. Because Haiti, though it had its independence, people who were going to the university, many of them went and they studied in Paris. So this was designed by a Haitian architect. The forms are very French and European. However, the forms have been adapted for the Caribbean in that the entire first floor, there are no windows, there are doorways all around on the first floor. And the second floor has these large windows that have got shutters on them, so they can promote ventilation through the entire building. And these buildings are extremely comfortable to be in on a hot Caribbean day with a cool breeze. And these are some I pulled images off of Facebook, so I can see what they're doing at the Maison du Fort. And they usually have musical performance on the outside. Okay, the second project I wanted to share with you is the Maison. This is a later gingerbread house, also designed by a Haitian architect. However, in this particular example, there has been a large two-story promenade that is made out of reinforced concrete that has been built around the outside of it. And in most cases, something like this would have destroyed this particular building, but since the building is almost completely surrounded by concrete additions, it actually held the building in place. By the way, this photograph was taken 10 years after the earthquake, so this is a recent project. And when I was working on this building, there were squatters on the inside of it, and I had to get to know the people who were living there, and some of the children were helping me with my analysis. This is a photograph of the inside of the building. So this building has been standing for 10 years, except is being rehabilitated. You can see the openness of the atmosphere and the damage to the exterior walls. This is an image from that front. And to give you an idea of the way this building was constructed, the walls in red are from the original structure. Those that are pochade in pink are the reinforced concrete additions, which I believe have helped to hold this building together. And for this particular project, we took a little bit more of a well-known seismic rehabilitation technique. We were picking areas where the masonry walls were damaged, and we were picking areas where we could put in shear walls. And so these were areas where we located shear walls. The shear walls that are being put in are not made out of reinforced concrete. They're made from confined masonry. That is, they put in a small column on either side of reinforced concrete, and then the interior is filled with masonry. And so it is a shear wall, but it's not quite as rigid as a reinforced concrete shear wall. And to give you an idea of what that type of thing looks like, these are the types of interventions that they were doing. My last visit there was almost a year ago. It was my last international visit before the pandemic came, and I was worried about being able to leave the country, and I've been able to follow what they're doing over social media. Second area I want to talk about is Bhutan. Now, Bhutan is located between India and Tibet, which is now part of China. So it's in this arc of the Himalayas, on the southern slope of the Himalayas. My project was located in Paro, which is where their international airport is. And I'm also going to talk briefly about the Wangdu Phadrang Dzong, which is here. So I was working these two areas here. By the way, for those of you who are able to join us during the first webinar, Professor Aaron Menon, he talked about his work at the Wangdu Phadrang Dzong. So the thing to know about Bhutan is it is an agrarian society. They have no industry. And if you need wood, then you have to arrange to have the wood felled, and they mill the wood right on site. And that's what this gentleman is doing. He's milling the wood on site. They use hand tools almost extensively, almost exclusively. And another aspect is this particular of Bhutan, they use rammed earth construction, and they still use it a lot. This is a photograph of the dedication of the building that's going up, and obviously I think this woman is one of the queens of Bhutan. But this is something that you will see pretty much everywhere as you're driving around. And here they put up the formwork on either side. They normally lay a horizontal wood member within the rammed earth wall. That's something that's important to remember in this talk. And then the roof is actually separate from the rest of the building. You see the roof is sitting on the building. So during a seismic event, the roof is not going to be bringing a whole lot of mass to what's happening there, because it's going to be moving separately. So I'm going to talk about the Sito Gumpa. This is a monastery. Here is the temple itself and the monks' quarters on either side. Here you're looking at the temple straight on, and here is on the other side. The temple has these beautiful paintings on the inside that are placed on paper. So this is what the floor plan of the entire monastery was like. And here is the temple. The idea was to seismic rehabilitate the temple, and these areas here were rehabilitated. Actually, they were reconstructed. They pulled them down and rebuilt them on site, because you can do that with rammed earth. One of the things we did was added a separate kitchen and dining room down here to complete the courtyard, because they had the kitchen was on the second floor of this structure, and we were really worried that they were going to burn it down. They have problems with fires here, so this was the plan for the entire one. These are some of my partners in crime, Chuning Dorji and Karma Wangchuk. Sonam Tashi is not in this photograph, although I hope he has called in this morning. He is. A shout out to Sonam and Chuning and Karma. And this was the idea that we came up with for the temple. The temple did not have any horizontal members in it, so we decided to introduce them. These walls are about 1 meter thick, and so we were actually carving into the wall, and we were putting these wood members on the outside and on the interior. We were connecting them with metal ties. It was fairly easy to do with this rammed earth construction, and then we wanted to wrap the whole thing with a band. And beginning of the project, we had a long 4-hour ceremony that included ritual dancing and a feast where all the villagers came in. And then we went to work. Here's the inside of the temple with all of the paintings removed. I believe those are some of the paintings there that are wrapped up in the paper. And so you can see now that a lot of this area has been reconstructed, and here is the temple, and here is where we're cutting in, and we're installing the wood. It's going in now, and here is the entire group of people that were working on the monument. Here's Sonam, and here is my favorite plumber, and the entire group of villagers that were working on this. We had to wait until we were off season because all of the villages are rice farmers. And the exterior of the temple, you can see that. And here's the last part where we're actually wrapping it with a polyethylene strap. It's the same material that is used for seat belts in a car. Then they were covered with this is a clay parging on the outside. Everything is clay, and you can see that we are actually leaving the strap exposed in these particular areas because we want people to be able to see what the actual intervention is. And here we're finishing up this project. The paintings went back in place. The ritual we had to dedicate the new temple, and that's the completion of the Sito Gampa monastery. And in the last 1 minute, I'm going to quickly show you the Wangdu Phadring Zong. This is an administrative center that has a series of courtyards, and the important aspect here is this building here called the Utsi. You can see the Utsi here. Building unfortunately had a fire in 2013, and it was the interior was destroyed, and particularly the Utsi, which is gone here. And we were there in 2013 trying to tout traditional techniques for the seismic retrofit. And Professor Mann talked a little bit about that, but what I wanted to share with you is that this particular Utsi, what they did is the Swiss offered to give them the money to put in a base isolation system. So the Utsi was completely reconstructed. It's got a base isolation system underneath it. I was allowed to visit this project during its reconstruction, and I was also allowed to climb underneath the Utsi to see the base isolation system, but I was not allowed to take any photographs. I think it's the only base isolation system that was put in the Himalayas. And so with that, I'd like to say thank you, and open to questions or to go to the next speaker. Thank you very much. You're muted, Tim.
Thank you. That always has to happen once during a webinar, right? So all the rest is now on notice. Thank you so much for your presentation, Steve. We will not go to questions just yet. You can post your questions in the Q&A or in the chat. Also, welcome to all the people who have just joined. I noticed some of you joined during Steve's presentation. Feel free to introduce yourself in the chat. We would like for this to be an active participation webinar. And so we will move on to our next presentation, which I'm personally very excited about because Mehrdad Hejazi is going to address one of my favorite traditional structures. Mehrdad is a professor of traditional structures in the Faculty of Civil Engineering at the University of Isfahan in Iran. He's an expert member of ISCARSAH and the chief advisor to the Iranian Ministry of Cultural Heritage, Handicrafts and Tourism. He has been the director of structural restoration of a number of national and World Heritage sites in Iran. He has published 6 books and more than 46 journal papers and 116 conference papers, mostly on architectural heritage. Welcome, Mehrdad.
Thank you very much, Tim. I hope you have my voice.
Yes, we do.
The subject that I'm going to explain is about traditional construction techniques in Persia to mitigate earthquake effects. And my case study is in Persepolis. First, I will give you a short introduction, then we go to Persepolis, then we go to nearby ancient sites, then we go 200 or 300 kilometers away to Susa, and again we return to Persepolis. Well, if you have a look at the map of the country at the moment, is the but when you go for 25 centuries ago, the first Persian Empire was so large. And here, Susa and Persepolis were the capital of the empire. I'm going to make a talk about Persepolis, and then I go to Pasargade and then to Susa to see what was the construction methods in that era. If you have a look at the microzonation of earthquake in Iran, you can see here that Shiraz and also Susa is located in high risk zone for earthquake. First, let's have a look at Persepolis. It's quite a huge site, more than 120,000 square meter, the area, and its construction took about 100 years. And this is what we see today. As you can see, the site is constructed on a high platform, just adjacent to a mountain here. And if we go back a few centuries ago, say 25 or 23 centuries ago, this was the situation it had. And it is very important that this site was not a governmental site, but it was a ritual site for celebrating the New Year, which we call Nowruz in Iran, and it is on 21st of March. Since then, still we have the same ceremony, and it's a very important ceremony for Iranians to celebrate that. Therefore, the Persepolis Palace was very important to Persians. It's a situation at the moment. These are the remaining of the site. There is a World heritage site. It is very well preserved. And even there have been some researches to the building, to this site. For example, if you have a look at the plan, you can find the golden proportion there. It means that the design of the plan and other dimensions were based on some ratios, mostly on golden ratio. Let's go to see how was the foundation built at that time. As you can see, the foundation was built in several layers of stone, as you see. And these stones were connected with flexible metal connectors. We see the same procedure, the same method for other sites. Well, if you have a look here, even at present, you can see the metal connectors which connect the stones together, and still it works. Let's go a few kilometers, about 10 kilometers away from Persepolis to Pasargadi and Nakhchi-Rostam. Here is Persepolis near Shiraz. Then we have Nakhchi-Rostam about 1 kilometer, and then about 9 kilometers away we have Pasargadi here. This is the remaining of Pasargadi Palace. And this is the tomb that most of you know. It's the tomb of Cyrus the Great. And if you go to Nakhchi-Rostam near Takhti-Jamshid, near Persepolis, you see some sort of stone tower which worked as a calendar for the new year and some sort of ceremonies. Let's have a look at the foundation. We start with the foundation of the tomb of Cyrus. As you can see, they dug the ground. They went for 1 or 2 meters down. Then they put the first layer of the foundation, which was stone, and then they put the second layer or the upper layer of the stone. They were just put together with no connection. You see the same technique used in that tower here. The first layer and the upper layer on the ground level, and also on other buildings. As you see, when you have earthquake here, you have some sort of acceleration or some sort of movement, if you want to say. And when you have two layers of foundation, they can easily slip against, and somehow they can dissipate the energy of earthquake. It's the same rule in the buildings, in the sites, in Achaemenid period. For more than 3 or 4 centuries, they ruled the country. Let's back to Persepolis again. If you have a look here at one of the walls, it is not a wall. Also, it acts as a platform for the superstructure. Here you see irregular cuts have been used for the stones, and you have irregular joints. Again, the architect had this idea that give the possibility of movement to the stones in case there are some movement of the ground. These stones are free to move without damaging the superstructure. Let's go to the columns. If you have a look here, there is a special connection between the main part of the column and the support part of the column. It's like this. Again, there has been a connection between the two parts in order to make it possible to rotate somehow, because it's at the moment with this technique, it is not a rigid connection anymore, but it is somehow semi-rigid. It means that if the top of the column would like to move somehow, it is possible at the bottom that you have some sort of rotation, and it prevents from a cracking or a breaking of the stone. And again, if we go for the beams here at the top, if you look, the beams were wood, and it's like this, okay? And again, here, you need some sort of freedom for both movement and rotation. And therefore, they didn't use a very rigid connection here, but they used some sort of semi-rigid connection in order to allow the top beam to rotate and move in case of earthquake. And in this how they were able to dissipate the energy of the earthquake. And more important is the rigidity of the whole roof. They use some sort of wooden roof in order to make a rigid diaphragm at the top, in order to make all the columns have similar and same movement at the top, and they make it to move in a similar way for the all columns. And having a rigid diaphragm or rigid roof is very important for those tall columns. Let's go 2 or 3 kilometers away to the west to Susa, which is here. It used to be again the capital of the empire in some time. Here you see the one of the palaces here. This is the site. Here is another palace, 1 or 2 kilometers away, and in the middle is the mausoleum of Daniel in Susa. Well, this is the aerial photo. Here to the right is the Apadana place of Susa, very old one, the tomb of Daniel, and to the left is the Shahur's palace, which was built about 200 BC. This is again the situation, and maybe here you can see this is the Daniel mausoleum, and here the Sapur, and to the bottom that you can see is the older part. If you have a look at the topography of the system here, to the right you see the old palace here. It was very old. It was 24 centuries ago it was built. If you have a look here, the ground level was here, but they decided to bring the level about 4 meters up, and from here they started to construct the new palace like this. If you have a look here, at the bottom, very bottom, you have the remains of heroes from the previous period. And they add some sort of sand or gravel layer here for about 1 or 2 meters. And from here, on the top of the sand layer, they started constructing the site or the palace with columns of about 22 meter high. And again here, when you have sand here, is some sort of base isolation here in case you have some sort of acceleration or movement in the ground. These sand or gravel layers prevent the energy, the total energy going up to the main building. Let's come back again to Persepolis. I'm going to give some talk about the sewage system, because I think the sewage system is somehow related to the foundation system of the site. If you have a look here, this is the site, and when you have heavy rain, it's like this. Therefore, for such a huge site, you need to have some sort of sewage system in order to drain and somehow convey the rain and somehow the sewage. And this is what they found a few years ago. As you can see, there is an underground sewage system. As you can see, it was discovered a few years ago. And 2 years ago, we had a very heavy storm and rainfall there. And you can see it worked at that time. It means the city of Shiraz and nearby Mardar city were both flooded. But it was interesting that Persepolis was not flooded. If I can show you this, you should see a movie which shows how the water is running inside the sewage system. This is at the same time that on the floor of the site, there is no water, but 1 kilometer away, nearby city, there was flooded and many people had to leave their homes. It means that it is not just sort of foundation for earthquake, but also the design of foundation for the flood or for the sewage system is also very important. Okay, let me finish my talk with the memory of ISCARSAH visit to Persepolis in 2018. And I should give you some references here. There are 5 books that I, with my colleague, have written, and also there are some papers that you can find also in the references. And also it is my email address in case anybody would like to contact me. It is possible to contact me. I thank you very much, and I hope you have enjoyed my presentation.
Thank you so much for the wonderful presentation, Mehrdad. Again, if you have questions, you can post them in the Q&A or in the chat, and we will discuss them at the end after all presentations. And so now we will move on to the next presentation, which is by Fernando Peña Mondragon. He is the head of the structural engineering department of the Institute of Engineering at UNAM in Mexico. Fernando received his doctorate in seismic engineering from the Politecnico di Milano in Italy and did a postdoc at the University of Minho in Portugal. He has published a multitude of scientific articles on the seismic vulnerability of historic masonry, and he is the treasurer of the Council of the Mexican Society of Structural Engineering. Welcome, Fernando.
Thank you very much. I will talk to you about some lessons that we have obtained from the earthquakes that hit Mexico in September of 2017. So, but first, I would like to acknowledge my team, especially my colleagues, Professor Marcos Chavez and Professor Natalia Garcia, and our army of students and project engineers. Here is the last ones which they participate with us, but there are a lot of many students and engineers that work with us. In September 7 and September 19, 2 large earthquakes hit Mexico and left 2,340 damaged architectural heritage buildings throughout the country, especially in the center and south of the country. So this is really a huge number of damaged buildings. So I would like to focus that this number is only the listed buildings that in Mexico are considered as architectural heritage, but there are a lot of small houses and particular buildings that are not counted in this number, but that they are part of our ancient structures. So this number is almost the 6% of all the architectural heritage listed in this region. So it's really, really a huge number. So after that, we made a survey of trying to see and understand the different damage that occur in these buildings. For example, this is the common damage in churches. So there are many churches of these types, some small churches of one nave, and really practical all the towns in Mexico. And we found in general this type of damage. So in the facade is particular only in plane damage. Practically the out of plane damage is only see in the frontispiece due to the overturning of the frontispiece. And this is a really interesting picture. For example, this is a diagonal crack due to the shear stresses in the tower. And this is a front view, and this is the other part of the tower. So it's like that the tower has cut by a knife, no? So we don't understand why don't collapse this part of the tower. And besides, there was a street, and the street was closed because the vibration induced by cars and trucks that are passing could collapse the tower. So this is a typical damage in a lot of churches that we found. Another typical damage in domes and drums, there was the typical cracking that we can see in literature with radial and meridional cracks. Some domes were collapses, or shear stress damaged the drum. Bolts have also the typical damages that we can find in literature with these longitudinal cracks, especially due because the walls that support the arcs and the bolts opening, and that's the reason to find these longitudinal cracks. After in walls, we can see the typical diagonal cracks due to the shear stresses. At the base of the walls, we can see these horizontal cracks due to the flexural moment in the out of plane of the wall. And we can see also these vertical cracks that is due to the shear stresses. And these vertical cracks were found when the masonry was very bad quality, especially when it was made by pebbles with pebble stones and earth mortars or very bad mortar. So another damage that we can find in some buildings, especially we focus on the monasteries that were attached to the churches that we visit. So it's of course, the collapse of the roof. So the overturning of the center of the walls, like in this case. And this particular case is very interesting because it was the cloister of an ancient monastery, and all the second floor was collapsed. So we can see here all the debris of the second floor, but this is how the material go down to the yard. So in this particular case, the masonry was very, very poor, made by rounded stones, pebbles, and a very, very weak earth mortar. So from its origin, the masonry was a very bad quality. And with when we have very bad quality masonry, we can found a collapse mechanism. The structure disaggregate completely. So when the second floor completely collapsed, the material has behavior like a fluid, and all the material was concentrated in this part. So this is how the convent was after the earthquake. Fortunately, in this case, was no any death or some person injured, but this is a very dangerous behavior because in the earthquake, this is a very fragile behavior. So the conclusion of the observed damage in this survey that we made in the different regions that has struck by these two earthquakes was the damage patterns and collapses that we found were similar than those observed in past events. This is, for me, very impressive conclusion. So we don't found new behaviors in the seismic behavior of the buildings. So we know the behaviors. We know from the past events the different types of damage and the collapses. So, for example, big towers, bolts, and domes continue to be the most vulnerable elements. So these three elements of the churches is always the elements where we have a problems of damage and especially collapses. And of course, like in some cases, the collapses were due to poor quality of the masonry. So from this, in general, in Mexico, intervention projects are based, of course, in the ICOMOS and ISCARSAH recommendations. But authorities and practitioners take for particular recommendation from all the universe of ICOMOS and ISCARSAH principles and recommendations. So especially authorities recommend minimal interventions, non-invasive techniques, use of compatible materials and techniques, and of course, traditional materials and techniques are preferred. But unfortunately, this four recommendation has become as the best project is to return the structure to its original conditions. So the idea in general, in practically all the intervention projects in these damaged structures is trying to return to original condition of the structures before the earthquake. So what can we expect from an intervention whose objective is to return the structure to its original conditions? So we have evidence of past events. Here I put only 3 particular events that damage a lot of structures. For example, in 1973, 1980, and 1999, we have 3 earthquakes similar to those that occur in 2017. And we have always the same scenario. So a lot of damage, a lot of collapses, the same kind of damages, the same kind of collapses. And someone said, insanity is doing the same thing over and over again and expecting different results. So if we try to restore the structure to its original conditions, we know what will happen with these structures in the next seismic event. We will have the same damages, we will have the same weak elements, we will have the same collapses. So now we are trying to change this paradigm in Mexico. Actually, the paradigm is, the aim of the project is the conservation of the authenticity of the architectural heritage. So here we don't have time to discuss what authenticity it means. But this is the idea here in Mexico. So the best project is try to conserve the authenticity of the architectural heritage. However, we need to change this because sometimes we forget the most important aim of the engineered structures. So is that the safeguard of human life. In this particular events, seismic events, we have really few deaths and injured persons because the earthquakes hit in an hour of the day and in a week of the day that there was not a concentration of people in, for example, in the churches. But if this seismic event hit in a Sunday, in the at 12 o'clock, when almost all the churches are full in the mass, so there was a really tragedy in Mexico because it was collapsed and killed a lot of people. So we cannot forget that the most important aim of any intervention must be the safeguard of human life. Thus, taking into account this idea, we need that the criterion to be followed is not just trying to return to the authenticity and conserve the authenticity of the structure. Instead, try to use a cost-benefit criterion. So cost, of course, is not only economic cost. So what we can lose if we choose some particular technique or material in the intervention, of course, loss of authenticity. We cannot forget that in any intervention project, we need to conserve the architectural heritage, all the implicit values in that the building contains, like history, artistic values, architectural, historic, etc. And we must put in a balance, so this cost, what we will lost with an intervention, but at the same time, what will be the benefit? So the benefit in the human life, safeguard of the human life, of course, conservation of the authenticity, conservation of all the values of the buildings, benefits in the structural behavior, etc. So we need, as engineering projects, just remember that always the capacity must be greater than the demand. Capacity in the sense of strength of the structure, ductility, deformation, etc. And demand in the sense of loads, displacements, etc. And remember that the aim of any intervention project should be, in the first place, the safeguard of the human life. In the second place, of course, preservation of the building value, artistic, historic, architectural. And of course, we should limit the damage in the structure. So if we change the paradigm and we don't forget the human life, we will preserve the building value. Because to preserve the safeguard human life is, for example, that the structure will not collapse. If the structure will not collapse, the building value will conserve. Unfortunately, at least in Mexico and in many practitioners that are involved in this area, they think that it's mandatory to try to conserve a structure in its original conditions. However, it's a very open discussion that what original condition means. So we know that any intervention that we make in a building, even the small interventions, will change this idea of originality. So we need to change, we are fighting to change this idea, and remember that the most important is the capacity much bigger than demand. Of course, with three aims. No? Don't forget, of course, the preservation of the building value. So, how can improve the performance of the structure? We can improve increasing the capacity, decreasing the demand, or at the same time, increasing the capacity and decreasing the demand. So, in this context of cost-benefit criteria, so we need to focus on solving the causes and the problems and not only solving the symptoms. We can find a lot of intervention projects that we have some cracks in the structures and the practitioners just only want to close the cracks with some material, and that's all, and the structure is okay. But this is not to solve the problem, because we need to understand what was the structural behavior to have these crack patterns. So we need to understand first the structural behavior, and after try to propose an intervention project. Of course, it must be based on the current conservation criteria. But we must follow almost the modern criteria of structural analysis and design. We need to incorporate the new tools that we have in structural engineering, in the seismic engineering, to study and to conserve these kind of structures. So a technique or some material may be good for one case, but not for another one. And in this particular case, for me, I don't like to divide the materials and techniques as traditional or new, because this has allowed this idea that only the traditional materials and techniques are good for the intervention in this kind of structures and return to the previous state before the earthquake. But if we use exactly the same materials and the same techniques, for example, in the case of this cloister that collapsed all the second floor because the masonry was a very bad quality, in this particular case, the authorities and the engineering project that are involved in the reconstruction of the building wanted to use the same kind of masonry because it was its original material. And this is a really bad mistake because we will have the same problem in the future. So if we will reconstruct the second floor of the monastery, we should reconstruct with a better performance than before. So the selection of the technique and material will depend on how we will improve the structural behavior. We need just to remember this part, that sometimes we forget because we are involved in another question, but sometimes in the intervention project, we forget this simple idea. Always the capacity must be greater than demand. So how we improve the structural behavior is what material and what technique we must to use. Of course, taking in account all the conservation criteria, taking in account the conservation of the values of the structure, but improving the structural behavior, improving the seismic behavior for don't have first any collapse. If the structure collapse, means that the intervention project was failed. So the first point that we have in mind is that the structure must not collapse. So just as a summary of this idea that I want to share today with you, is that in Mexico, at least in Mexico, we need to change the paradigm. And don't forget that the most important aim is the safeguard of the human life. And after that is the conservation of the all values of the structures. So the structural intervention must improve its structural response. So if we have collapse in the structure, means that the structure have a very bad seismic behavior. So we need to improve this, because if we made exactly the same, we will have exactly the same problem. So due to the two earthquakes that hit Mexico in 2017, we have really a lot of damaged buildings, and Mexico has not the resources to conserve all that or to intervene and restore all that buildings. After 3 years of the events, we have almost 1/3 part of the structures that has not been intervened today. So this is a huge problem. So we need to improve the structural behavior of our structures. And of course, it's not to return the structure to its initial condition, because it means that the initial condition is not, has not good performance. And we need to remember that any intervention will modify the original structure. So any intervention that we make, we change the original structure. So it's really complicated, just this idea to return to the structure to its original conditions. Of course, the intervention project must be multidisciplinary, because the structural engineering is an important part to increase.
Fernando, sorry to interrupt. We're going to have to move on very soon to the next presentation in order not to go over time.
I will finish now. This is the last slide. So the intervention project must be interdisciplinary. So of course, to trying to safeguard not only the human life, but also the value of the buildings. And each problem is unique. So we can make some general rules that this is another problem in the practitioners that wants a general rule to solve their problem. And we propose that a cost-benefit criteria must be followed. Thank you very much.
Thank you so much, Fernando. And I think you're raising a bunch of really interesting topics that we will touch on in the discussion later. For example, that your distinction between traditional and modern methods, and especially when you bring up authenticity and human life. I would like to point out to all the attendees that ISCARSAH will be putting up a specific webinar on authenticity and reconstruction at the end of April. You will get the information about that in a few weeks. I would also like to encourage people who are watching our webinar through Facebook Live to post questions there. We are monitoring your questions and we'll address them at the end. That said, we will move on to the next speaker. Amina Abdesamed Fufa is a professor of built urban and natural cultural heritage with a particular focus on heritage at risk due to earthquakes, landslides, and flooding. She is also the director of the Research Sciences Laboratory of Environment and Technology for the Architecture and Patrimony at the Université de Blida 1. Aside from being a professor, Amina is also an active professional architect of built cultural heritage and historic sites at the Ministry of Culture in Algeria. She has supervised many restoration projects and is currently in charge of the restoration of the Palace of the Dey and Palace of the Beys at the Citadel of Algiers, which is a UNESCO World Heritage Site. Welcome, Amina.
Thank you, Tim. And good evening, everybody. Thank you very much for the invitation. And I'm here, I'm happy to share with you the experience of the North African countries, and in particular the Maghreb region. So my talk today is about earthquake-resistant techniques from ancient time to 20th century in the Maghreb region, where I will present the case of Algeria, Tunisia, and Morocco. So all over the world, buildings located in risk-prone, in seismic-prone risk area are almost and exclusively constructed on the basis of the experience and observation of local builders. The people living in this risk region has developed over time many strategies to coexist with this phenomena, in particular social behavior and constructive approach aimed at preventing and limiting the exposure of buildings and inhabitants. The concept of local culture encompasses the social and technical dimension of the act of building and the process of developing the knowledge and its skills. The vernacular way, the vernacular as a way of living, as a characterization of construction and self-protection methods, turn out to be a valuable source of practices, techniques, and measure proven over the century, and of the many of hazard for the construction of a sustainable built environment, accessible and secure. So this is the this map shows the distribution of earthquake in the Mediterranean basin, and we noticed that the most event are located in the west and central region, when we have the seismicity of the northern Maghreb is light to moderate, and those moderate seismic hazard countries. Except the recent earthquakes which happened during the 21st century, Maghreb countries has experienced in the past several moderate seismic events that caused loss of human lives and damage to property in different regions. The historical earthquake knows since ancient time to today greatly increased the probability of an earthquake occurring and damage in the future. So we had 3 great earthquakes that happened in during the past. The 1716 earthquake of Algiers, the 1624 of Fez, and 1785 of Tunis. So based on this information, fundamental question of interest for the architect and engineers are: how did the local population build their houses resisting earthquake loads? And what structural techniques did the local population use for building their house to protect themselves against earthquake? Of the earthquake resistant techniques in the north part of Africa, and here in the Algerian country and Morocco and Fez, and we have all the techniques are located in the coastal line, and some of them are located in the highland, in the west highland of Algerian country. The techniques developed are of 2 scales. The first are architectural and urban concept, and the second are the constructive. So we have architectural design, urban design, such as the sabbat, discharging arches, vaulted basement linked by arches, and from the details we have the reinforced masonry with wooden logs, reinforced masonry by layers of bricks, and reinforced rammed earth. During the Ottoman and in the Idrisid period, the 3 cities, big cities, Algiers, Tunis, and Fez, showed typical characteristics of medieval Muslim cities, where building blocks are a lot of various size. The plots are fully built, and the houses are leaning against each other, constituting or forming a compact unit, forming a narrow street, which are covered by galleries. And sometimes they are built with, they are vaulted, or they are built by roof. So this passageway are called sabbat, and beside, we have the block, which are linked by arches, and this different characteristic of urban design constitute a structural continuum. So when the passageway are vaulted and they connect between the houses, this is a passage which is connected with the two parts of the two sides of the houses, and we have here in this picture, in this slide, different case of the connection between the passageway and the houses, and this continuum, structural continuum, which dissipate the seismic load. We have different cases with just a basement and in the higher part of the building, we have three volts between the two parts of the buildings. So there are two series of cross volted inside and outside the houses, which connect between the two blocks. These are different examples of Algiers, covered passageway with roof, vaulted building, vaulted passageway, and here we have the Sabbat. We have another Sabbat at Tunis, and the arches connect, discharging arches. We have buttresses and fairs. In this picture, the different arches, discharging arches, and connecting buttresses with blocks of wood, which connect between, which maintain the building in order to not overturn. During the 20th century and during the French colonization, the recommendation of the 1844 by the military engineers for the construction of Algiers, they prescribed as well for the private and public construction the low buildings because of the seismic risk, and to vault the basement and to join the building between them by arcades. I'm sorry to not present. I lost my photos recently, and unfortunately, I did not have time to go to the site to take another picture. But it is written in the military engineers report that Algiers has been built taking into account this disposition. So, from the part of the constructive detail, some of techniques were discovered or was highlighted during the investigation, in situ investigation in the territory, in the Algerian and the Maghrebian territory. So here we have an ancient time site of Caesarea, located in Algeria, and these techniques where we have a superposition of two layers of stone and flat brick. Is not a brick, but it is a plate made of brick. And which is located or disposed on all the depth of the wall, and it is put in regular. We have regular disposition in this and it is.
Amina, sorry to interrupt for 1 second. Amina, could you try to turn off your video, because we have some problems hearing you, maybe because of the internet connection. If you turn off your video, maybe the audio quality will be better. Thank you.
Sorry, Tim. What is the problem? You don't hear me.
We don't hear you very well. Your sound goes in and out. So I'm worried it's the quality of your internet. So maybe if you turn off your video, which should be on the bottom left of your screen, you can maybe turn that off. If you don't find it, we can just, yes, perfect. Thank you. Can you continue?
Yeah. Did I repeat or I continue?
No, you can just continue.
Okay. So this is called is an open system where we have two layers of different materials, and these stone tables are superimposed on the stone masonry. So this was an ancient techniques used by the past. During the medieval period, we have the rammed earth reinforced by wooden blocks. This kind of techniques was used in the city where the Moorish lived, because in the city where we have found these techniques, the Moorish lives during the summer, and they have developed this technique of construction for the people who are living in the city, and this is part of the walls, the surrounding walls of the city, and we can see the rammed earth reinforced by logs of wooden logs. During the Ottoman period, and we found the techniques of the construction of foundation of the column. We have superposition of two perpendicular layers of tuya, which is a cedar wood, and these logs of wood has the role of shock absorber, and it minimizes the amplification of ground acceleration. This is one of the techniques of the energy dissipation of in the foundation. The vertical structures, such as walls, we found that the wooden logs are inserted in all the depths of the walls, which are made of masonry, and we can show that in the walls here in Algiers, and this is in the site of Tunis, and these are in the site of Fez. We have also this kind of techniques reported in the pillars in Algiers and Tunis, and we have also the chaining at the angle, also in different cities. So here we have the chaining of the wall. We have these techniques, or these logs are put in this manner, and they where the greater fragility of the walls is due to the combination between bending effect and shear and torsion. So this technique diminuate the effect of torsion, and the angle did not collapse. Algiers, there is a particular techniques in arches. They are reinforced by logs of tuya, and we can find sometimes one layer when we have only the arches, but we can find also two layers of logs of tuya when the column are supported masonry vault. This superposition of two materials, one rigid and the other flexible, guarantee due to the slip movement or rolling, which is a good resistance to shear during earthquake. And those the system of arcade is contribute to the resistance of earthquake loads. This is particular to Algiers. Haven't found it in another site. This is the galleries of houses in Algiers. The other is in Fes, and the other one is the site of Tunis. Logs are also used in the dome and cupola, and you can find these logs here and this part. They are playing the role also of shock absorbers, and well, the other techniques which is different from the reinforced masonry with logs of tuya is the earth bricks. And this is techniques which was used in the city built or constructed by the Moorish when they arrived at Algiers after the Reconquista. So during the 16th century, we have this earth reinforced by bricks. And it was, this technique is called tapia valenciana, and it was evaluated by Cristini in Spain as a seismic resistant techniques. And it was used at Valencia after the great earthquake of 95 or 59, 1359 earthquake. Later, during the 19th century, this same techniques was used in the colonial buildings, such as resistance techniques, and at my city, at Blida, because Blida is located in a very high risk area. We have the fort, Soma Buinan fort, which arrive until the city, and Blida was destroyed several times in the history. The first recognized, the first important earthquake was the one of 1725, earthquake, where all the city was destroyed. And then the reconstructions was, during the reconstruction, all the houses were built with the tapia valenciana. And when the French were in Algeria, they used this technique because they know during this time that the city is seismic area. And in the in other region, in the highland of, in the West Highland, we discovered a system which is, we called traditional warning system. This system is made of, it's built with beam of with logs of trees, and the hooking system of wood element. They detached when soil movement happened, and this happened not only when the earthquake happened, but also when we have a landslide, because the construction are on a sloping soil. So we have these techniques was used in the historical mosque during the 17th century, and this the seismic activity in this region was known as the first known earthquake was the earthquake of the 1858. And during the restoration project, as today we are talking about the reuse of compatible materials, of historical techniques. We have reused the techniques using the logs of wood inserted in the masonry and in the columns. So we have here before the restoration and here after the restoration. It was really difficult to us to reproduce and to reuse these techniques, because in Algeria our regulation is still dating from the 18th, from 1918. It was the regulation was made after the El Asnam earthquake, and during this time the restoration was made over the world by the reinforced concrete. So the techniques of the post consolidation are still today in our regulation with the reinforced concrete. But today the research has evolved, and with our students, we are now working on the basis of the Eurocode 8 for the masonry building, while waiting to develop our own regulation for historical building. So the Citadel of Algiers today is restored according to the European code and not following the Algerian one. But it is not easier because for us, because the regulation, the Algerian regulation, is still applied today, and we must to circumvent it. This is a picture showing the shaking table test that which has been done during the Perpetuate project, seismic preservation of historical building, where Algeria contributes, and we have they have a mosque at Algiers. They is located at inside the Citadel of Algiers, and the prototype collapsed at the ground acceleration of the recent earthquake of Algiers. Yes, it was collapsed because the prototype was isolated. It was not connected with the other part of the building or the other part of the construction, but we have just simulated a part of the vault of the mosque. conclusion, it is known that the Maine has always know how to adapt to different natural risks, particularly earthquake. In the North African region, and in particular the Maghreb, earthquake-resistant techniques have been developed, although the moderate seismicity. Before the regulation from antiquity to the colonial period, earthquake-resistant techniques are different from one region to another. They constitute today the transferable indigenous knowledge in the Mediterranean basin. Thank you very much for your attention.
Thank you so much, Amina, for this wonderful presentation. It's also wonderful to see that parallels are being drawn in the chat between the techniques in Iran, for example, and then in the Maghreb. And it's something we can come back to when we start the discussion. Now I would like to introduce our last speaker, Jitendra Botara, who is speaking to us from New Zealand, where it's currently almost 4 a.m. in the morning. So thank you, Jitendra, for your dedication. So Jitendra is a Nepali based in New Zealand. He's a fellow of the Fellow of Engineering New Zealand and of the New Zealand Society for Earthquake Engineering. He's director of Recipro International Engineering, a New Zealand-based company, and has lectured and written extensively on seismic engineering and disaster risk mitigation. He has provided advisory services about disaster risk reduction, earthquake recovery, and reconstruction to many governments and international organizations, including the United Nations and the Asian Development Bank. He's an ardent believer in identifying strong linkages between social and seismic engineering for seismic safety. Welcome, Jitendra.
See here. So, video. Can you hear me?
Yes, we can.
Okay. So, give me a minute. Mute. This is covering my screen. And you can see my screen.
Yes,
my
we're
presentation.
all good to go.
Okay, good. Thank you, team, for the kind introduction. Good morning from the country of sunrise. Good day, good afternoon, good evening to all from around the globe. In my today's presentation, I will be discussing about my experiences and observations of last 2.5 decades on seismic resilience of vernacular construction along the Himalayan arc. I have two more co-speakers, Professor Jason Ingham and Dr. Dimitro Dijur, both from New Zealand, but I will be presenting this webinar. Thank you to ICOMOS for this opportunity to share my observations. In my presentation today, I will be discussing about identifying seismic resilient vernacular construction masonry building systems along the Himalayan arc, and I will evaluate their seismic resilience from current engineering perspective. My goal is not to romanticize or glorify the vernacular construction, but to scrutinize these because these are live construction in Himalayan region. But the fundamental question is, why should we study this vernacular earthquake resilient construction or vernacular construction at all? Because earthquake after earthquake, it has been proved these are very weak, highly vulnerable construction. Either you go to Himalayas or anywhere in the world. So why should we study them rather than discarding them and bringing something more modern, which can provide us better seismic safety? But in my opinion, and my observations in work in many countries, I believe this vernacular construction can provide disaster risk reduction in a sustainable way. When I say disaster risk reduction, I'm not talking about only natural disasters. I'm talking about cultural disaster, and I'm also talking about socio-economic disaster. So they are sustainable system because they developed over the time from the experience of the people. A large part of Himalayas is still very inaccessible. If we are talking about this vernacular construction, the knowledge base is with the community. We don't need to bring technical engineering knowledge from outside. The construction materials are there. So people have no dependency on importation of material. They are socio-economically more amenable. They conserve culture, and environmentally, they are environmentally sustainable because they require minimal energy over their life cycle. But of course, these building systems have their own problems, their own limitations that we need to understand. They can't fit everywhere, though they could be sustainable in certain context. So we need to understand this. But there are certain building types, say, along the Himalayas with certain earthquake resilient features, which has provided seismic safety over the centuries. And in each earthquake, they have proved their validity. They are validated by earthquakes. So let's look at the Himalayas. So from east to west, it is something like 2,400 kilometers long. And we all know Himalayas are seat of mega earthquakes. Many magnitude 8+ earthquakes. But let's look at the building types. So if you look from east to west, from Bhutan to almost close to Pamir, western Pakistan, you see a lot of building types which have survived earthquakes after earthquakes. Maybe some buildings are weak, some are stronger, but the most important thing is how intuitively, how intelligently people have used whatever resources they have to make this building earthquake resilient. So it is not a matter of weak or strong, it's a matter of how intelligently the system has evolved or developed. If you look at these building types, we can broadly classify these building types in two groups. One is earthquake-less masonry buildings, where timber runners or bamboo runners are laid along the length of the building, and they are tied together by truss members. And these timber members, these runners, tie whole building together as a box and provide box action. These timber members subdivide masonry in small parts. Thereby, it prevents widening of cracks dangerously. And then masonry and timber work together as a composite system to survive an earthquake or earthquake shaking. The other system, if you look at, is basically timber-framed masonry buildings. Good thing with this system is their walls are very thin, something like 4.5 inch to 8 inch, depending on brick or stone. They have timber frames with bracings, but bracing doesn't need to be X-shape. It could be any configuration, as you can see in the left photograph. Masonry is confined in small compartments, and masonry is held by timber. And masonry and timber work together to develop a composite system. And these both systems have developed over the time through the experience, and they have survived well. But of course, as I see along the Himalayas, there are more timberless system than the timber-framed system. Timber-framed system are mostly on Western Himalayas. Time to look at their seismic safety or do assessment. If you look at earthquake engineering or building safety, there are two ways for building to be earthquake resilient. Either building has to be very strong, or it must have deformation capacity. We all know these vernacular masonry buildings are very weak, because the masonry is very weak because of mud mortar, or many times there is no mortar. We can't make strong. The mortar we can't, because there is no alternative in many areas, or most of the areas, I would say. Connections of these buildings are, I would say, cannot be made rigid. They are semi-rigid. We can't make them rigid like welded or bolted connection. So they are relatively weaker than industrialized modern materials. But the beautiful thing is, the people have turned these weakness into the strength, so the building can survive earthquake shaking. So basically, people have adopted deformation route, provide more and more deformation capacity to the system, so they can survive an earthquake. It is something like saying, if I am flexible enough, if you push me, I'll just deflect. You can't push me any further, because I am deflecting. And that's how these buildings work. But the important thing is, we lack understanding of these building systems. These vernacular building systems, the earthquake resilient building systems, work differently than the industrialized modern materials. Buildings constructed of cement, steel, or rebars. And our building codes are written for these industrialized modern materials, which are mostly monolithic. So we can't apply these building codes to this vernacular construction, and every time if you apply, what we find is these buildings are unsafe or vulnerable, whereas these buildings have survived earthquake after earthquake. So we need to rethink our strategy or our approach to these buildings. Let's take one example. On the left, on the right, there is a building system, a base isolated building system. And what happens in base isolated building system, whole building remains as a rigid body, works as a rigid body without any nonlinearity. All the nonlinearity or deformation happens in the base and at the base isolated system, in the base isolated system. Whereas if you look at this vernacular construction, it's a stone in mud mortar, but with reinforced concrete bands. And you see how it works, because the mortar has it doesn't have any strength practically. So everything slides and rocks, and that's how it works. So let's see this small video. Where did it go? So the consequences are, because of our lack of understanding, the consequences are, here is a temple from Kathmandu Valley. It's a five-tier temple. This temple has survived 1833 earthquake, 1934 earthquake, and recently 2015 earthquake with minimal damage. All the studies completed until now I have seen shows this temple is highly vulnerable to earthquakes. But no study I have seen it to indicate why this building survived all the mega earthquakes. And that clearly shows we don't understand these building systems. So we need to develop new strategy to understand this building system. The fundamental philosophy, earthquake safety is life safety. So we can't apply current building codes or the standards to evaluate these buildings. So let's go to the fundamentals and look at these buildings from fundamental principles. Are these buildings really earthquake Shefa, or they meet earthquake resilient principles. So I evaluated these buildings from configuration, integrity, redundancy, stiffness, deformability capability, energy dissipation, and reduced seismic weight. If you look at configuration point of view, these buildings are very simple. Vertically and horizontally, they are very regular. Their windows are very small. The small window means there is a larger wall area to carry seismic force. They have very well-defined load paths, so the load can easily travel from point of its origin to the ground. If you look at the length to width ratio or height to width ratio, it is typically 1:2, and most of the standards would recommend this should be less than 3. So this building from configuration point of view are good buildings. If you look at the bottom left building, it is a circular building. And I'm not sure if you are aware of circular buildings, though unreinforced, performed extremely well during Gujarat earthquake in 2001. And this building is from West Nepal. Let's look at the integrity point of view. My observation in many earthquakes is one of the biggest reason of catastrophic failure of vernacular construction or even any building system is loss of integrity. These earthquake resilient vernacular construction systems have enhanced integrity. People have tried to use whatever they have, any resource, to improve integrity of these buildings. Other thing is they are flexible joints because they couldn't make rigid joints. But the beautiful thing with flexible joint is they flex, thereby release energy, but at the same time they do not overstress the connection or the connecting elements. So the controlled movement helps releasing energy, but helps building to deform. What about redundancy? Any resilient system, it could be even our family. If our family is resilient, that means it must have a redundancy plan. It must have backup system. These building systems have high redundancy because these buildings have multiple load paths. They have sacrificial elements. So for example, if you look at the left figure, left image, the part of wall has collapsed, but building is still standing well. So basically it is meeting its requirement of maintaining integrity. If you look at the central image, you can see how badly walls have deformed due to 2005 Pakistan earthquake or the Kashmir earthquake. And a few of the stones has already fallen off. Still wall is maintaining its integrity. So that means this system has very high redundancy. And redundancy is one of the traits of any earthquake resilient system. What about stiffness? One of the biggest problems I have seen in many earthquakes is the reinforced concrete frame building badly suffer from soft story mechanism because of obvious reasons. Though masonry buildings, these vernacular masonry buildings are flexible in nature, they have enough stiffness to avoid such type of failure. Of course, this can happen to these vernacular construction also if earthquake is a very long and very high intensity, but probabilistically that's very unlikely to happen. So these buildings have enough stiffness to survive earthquake, though they are very flexible. What about deformability? These vernacular construction systems work on the deformability, their capacity to deform. But if many elements, different elements deform in different way, And if they do not have compatibility, things would start breaking. The moment one element breaks, that chain of break failure will start, and that would lead to catastrophic failure. But the good thing with these systems is they are very compatible. Different elements are compatible. For example, wall is sliding, and the masonry units are sliding past each other. They are rocking like this. The joints are flexible or semi-rigid. So all this controlled movement avoids stress concentration in particular elements, thereby helps building to survive. What about energy dissipation? As earlier shown by many presenters, and you may have seen during many earthquakes, in the past earthquakes, masonry buildings have very large cracks like this. Because these cracks have to happen to release energy. Because earthquake is imparting energy to the building system. But what happens if there are seismic bands? There are runners or frames. Let's look at a video here with timber frame. This test was completed in 2018 when we completed a very extensive test on masonry buildings. So let's have a video. The acceleration of this video during shaking was 1G. That was the capacity of the table. It is a 230 scale model. And you can see how masonry is sliding past each other and units are rocking. So you can see through this sliding, it is releasing energy. It is like a friction damper or rocking damper. And the beautiful thing is, in the left figure, you see very large cracks. But mud mortar, if there are timber bands or some bands, some form of tying elements, the cracks are prevented from widening dangerously, because these bands hold the masonry together. And other thing is, beautiful thing with masonry in mud mortar is, because it is always in cracked state. So that means degradation is very low compared to high strength masonry. What about seismic mass? People have tried their best to reduce mass. For example, in the central figure, bottom 2 stories are masonry with timber bands, but top one is a light structure. Same in that, this is Dhaji Dewari or timber framed construction, say from Pakistan. And just by doing this timber frame, people have reduced seismic weight by almost 1/3 to half. So that's a significant reduction in seismic force. That leads to reduction in seismic force. What I mean is, people have tried their best to improve the system. If you put these all 7 attributes of seismic resilience in one figure together, what we see is more this shaded area, better the building is. So this is an unreinforced masonry building, vernacular building again, but have very little gray area. That means this building is highly vulnerable. Timber-laced building system is a much better than unreinforced masonry because very large shaded area. If you look at timber frame building, these are further better. But we need to understand these timber frames building are mostly 1 to 2 story, whereas this timber-laced building can go maybe 3 story or even more. So each building type has their own limitations and their strengths, and we need to understand that. So the conclusion is, vernacular building systems are sustainable building systems. And again, I highlight, when we look at sustainability, it is not only earthquake or any natural disaster. Sustainability means cultural sustainability, socio-economic sustainability, because these cards life, These are important tenets of life, not only the technology. Vernacular earthquake resilient building system can provide earthquake safety sustainably. So the important thing is to mainstream, promote these strengths and mainstream this construction system. Of course, as I mentioned earlier, these building systems have their own weaknesses and strengths. And we need to study these weaknesses to understand how we can improve them using modern technologies. So that should be our goal. Thank you very much. This is all about my presentation. And if you have any question, please feel free to ask. Thank you.
Thank you so much, Jitendra, for such a wonderful presentations. I particularly liked your analogies, trying to explain very difficult concepts with very simple analogies, and I think it gives us a great overview of why traditional structures can work well. So I would like to pick up on that now, and if you could stop sharing your screen so we can get all of the panelists on the screen, then that would be great. Thank you. And so we will go on for about another 15 minutes with discussion based on the questions that were raised. And first of all, I would like to go back to what you actually put on your last slide, Jitendra, and like the two signs of change versus go back to the same old. And that also brings me back to the points that Fernando raised about traditional versus modern interventions and rebuilding better. And I was also really struck, Jitendra, by your comment there that we should not glorify, one slide back, but better understand traditional structures. And so I wanted to ask Steve to comment on that interaction of new and old techniques in traditional structures based on different approaches that you presented, Steve. And maybe later, Jitendra, you can chime in on that as well.
Should I try?
Steve? Okay.
I think we'll go back to Steve first.
Okay.
Okay, I am here. I can't seem to turn on my video, but I'm here. And I'm interested in the compatibility of, okay, let's see, start my video. I'm interested in the issue of compatibility of traditional and modern techniques. I know that in the past, materials such as reinforced concrete has become like the bad boy in heritage conservation, and in many ways that is earned. But I don't think that we should always just say certain materials or certain techniques can't be used. It's really a question of compatibility. Now, in the presentations I did, in Haiti, I showed that we actually used concrete in the foundations. In Bhutan, we got this horizontal tie going, like what Jitendra was talking about, using a polyethylene strap, and that is because we couldn't go all the way around the building and tie the wood in the way that would have been ideal based on the building that we had. But I think that it is okay to look at contemporary materials and contemporary techniques. We should always start with the guideline of minimum intervention. But when we intervene on a building, as minimal as that intervention may be, it's going to be a change. So there's always going to be a change. Fernando was talking about the change and the change that we need to have. These are important topics, but we should always start with what is minimum. And the principles that are ISCARSAH principles, and also the guidelines we're working with, I like to look at these as guidelines or roadmaps. Is something that you can start with. If you're taking a trip, you may look at a roadmap, but then you may decide to go a different way based on what road or sites that you want to see. So I think that we can have some guidelines, but we don't need to have strict rules. I hope that answers your question.
It does. It does. Any of the other panelists, Jitendra, for example, wants to chime in?
Sorry?
did you have a comment on that as well?
I would like to add to Stephen. Compatibility is an important issue. And of course, as I mentioned, we need to understand limitations and strength of this vernacular construction and bring in modern science or modern engineering to improve them further rather than discarding them. And there is a lot of opportunities to do that. Because that time, if you look at historically, there are only 5 construction materials along the Himalayas: stone, semi-burnt bricks, mud, timber, and bamboo. But now we have more materials. These buildings are very flexible and they said stones or brick. So we can bring some confinement, polypropylene, or it could be wires or anything. But this system should be compatible with the existing system. So rather than destroying the philosophy of existing system or the vernacular construction system, we should be enhancing that properties, that characteristic. That's how I think. And we did some testing on that, some extensive set table testing. That could be one of the largest testing program in recent time on stone masonry, and we found fantastic results.
I think that's a great comment. Thank you. I don't know, Fernando, as this all started with you, I'm wondering if you want to comment further or if we should move on to the next question.
Yes, of course. I agree with Stefan and Sandra, and I like a definition of what means minimum intervention of Philip Garnier that write in the chat. I will read it. That he said that minimum intervention means maximum understanding. So that is the idea. So when I talk about the change of the idea, is that we are, according with the ISCARSAH principle and ICOMOS, and of course the minimum intervention is a part of this idea of intervention. However, sometimes for professionals involving the practitioners and unfortunately at the same time in some part of the authorities, they don't understand very well these principles. So in the academia is well spread and understanding and etc. So I try to show how the practitioners are thinking in Mexico, not the academia. So when I say that we need to change the idea, is the idea in the sense of first we need to know the structure, and knowing the structure is how to make the intervention, of course, taking in account the minimum intervention. And when I said that the general rules is not possible, I don't say that the guidelines is not okay. I agree with Stephen Kelly that it's a type of roadmap. But unfortunately, the practitioners take like a cook recipe that, okay, the first step is this, and I will do these steps in all the cases, but without knowing the structure, without knowing why the structure have that damage. So I think that one aim of the academy is to spread this knowledge to the practitioners and in the first place to the authorities. Because when I talk the authorities, is in all levels of authorities. In general, the directors of the institute that is regarding to conservation of the architectural heritage in Mexico, they understand very well these concepts and these ideas, how to conserve. But the low authorities that they are in field and they are working with the practitioners, sometimes they are not full understand these ideas.
Thank you so much. I would like to move on to another point that was made a couple of times in the chat. I think it was very well voiced by Fatemeh Sarraj, who said that many of the construction techniques that Amina was showing in Algeria were very similar to what you could find in Iran, for example. And I was wondering if Amina or Mehrdad could maybe comment on that transfer of technology and similarities.
I think that, yes, it's probable, because there is transfer of technology. I know that between the two sides of the Mediterranean basin, there is transfer of different technologies or different techniques of construction. But using the logs of wood in the masonry, I think that the last country, or the country that I'm sure that there is this techniques is Syria, because they discovered during the they discovered in Latakia that the historical building constructed after the historical major earthquake with the earthen, they reinforced the earthen, the rammed earth construction with wood, and it is written in logarithmic language. So I'm not, for the part of from Iran, I'm not sure, and I don't know if there is this similitude between the Maghrebian region and the Eastern region. So if possible, Mehrdad can explain to us if there is this kind of techniques in his country.
Yes, actually, I don't think that there is a need for transmission of techniques between the two countries, because first, the climate of Algeria is very similar to the climate of central Iran, which is warm. And also, the people in these two countries had the same problem. And also, they had both people in both countries were human beings, and they had their own knowledge. And therefore, to solve the same problem, they reached the same solution. That's simple. Probably, sometimes there would be some exchange of knowledge, but between Algeria and Iran, I don't think there have been such an exchange of knowledge during the history. And therefore, I think it's the same solution to the same problem. And that's it. The material is the same, the climate is the same, and also the mentality of the two nations are the same. I think it's just a matter of same problem, same solution.
I think that is a wonderful comment to indeed recognize that several of these techniques recur all around the world, and often people have arrived at the same solution because it just makes sense. With that said, and being mindful of the time, I would like to thank all of our panelists once more for making time to attend the webinar. I would also and speak at the webinar. I would also like to remind everyone that there is a third and final part to this webinar series on Thursday, April the 14th. And with that, I would also finally like to thank all of the participants for the active participation in the chat.
Namaskar.
Thank you so much.
Namaskar to all.